Another technical hurdle. It always happens. I haven't run my computer for a couple days. Everybody have a nice break. Good. We need more of those, right? All in favor of a 3-day weekend. So, okay, let's get started. So I wanted to begin. We're going to talk about the Metropolis-Hastings algorithm, but I wanted to begin with just how important this algorithm is. And I did a quick Google search on, what are the top 10 algorithms according to the IEEE. And there's a whole bunch of documents written like this. And so you're going to see different lists if you say the top 10 algorithms. But if you append IEEE, you're going to find the same top 10 list everywhere. So a long time ago, back in the year 2001, I took a class over in computer science at Stanford, and they had a whole class on the top 10 algorithms. I thought it was really cool. So people had gone through, the IEEE had gone through, and they had basically ranked these things. Exactly how they ranked it, you probably want to know what's their methodology, is it just people voting, so on and so forth. But at the top of the list, regardless, is this algorithm called the Metropolis algorithm. Now I've called it the Metropolis-Hastings algorithm, and I think that they're just not writing out the whole thing. I think they actually meant the Hastings variant of it. And so we will figure out what the Metropolis algorithm is. There are all these different variants. But in a nutshell, this is all called MCMC. So I'm going to say right here, the Metropolis-Hastings algorithm, this thing right here is Markov Chain. Monte Carlo. Some people have come in and said, no. This is, you can't make the equivalence here. And I really do stand by it. I mean, they're equal to each other. Every MCMC algorithm you know, or can write down, or has ever been come up with, is this algo, right here. And so, and I'll show you what the most general version of the algo is and what everybody's talking about. I really do mean. So, they're the same. All of MCMC is this one algorithm. So they might have put the Hastings contribution. Turns out, I think it was in 1954, Metropolis wrote down an algorithm. I'll write it down for you. And in 1957, Hastings came up with a more general variant of that algorithm. And eventually, I think next time when we go through the proof that this algorithm actually does give you what you want, I think Metropolis could have worked it out. And I'll show you how I always work out whether or not my algorithms are correct. And so I'll even give you the general flavor. So I've written down a few of these in my lifetime as well and published on them. It's kind of a fun game. It's like, my algorithm's not working, improve it. Show me what I need to do to come up with a general algorithm to improve. There's a whole bunch of other algorithms in here. Oddly enough, simplex is my second favorite algorithm as well. And so, does anybody know what it is? It's an optimization for linear systems. And so what I like about it is it gives you not just the answer to your question, what is the optimum, but it gives you also the answer to, if I release the constraint, how much would my optimal answer change? So it gives you kind of information on top of it. If I change something, what would happen? And so I really like that when you have that extra information. And so that's really what a Lagrange multiplier tells you. So this is also giving you the Lagrange multipliers. They've got a whole bunch of algorithms on here, and some of these you probably use. Fast Fourier is an all-time favorite. And so you could do slow Fourier, but doing fast Fourier is just better. So basically writing down the Fourier representation of something, giving you all of those different signals and where they're happening. Doing it quickly. Jack Good came up with a version of that algorithm. It was simultaneously discovered by a number of different sources, so Jack gets some credit there. So we've studied Jack in the past. So we should probably come back around to that question, who named Bayes? Who is all this named after? So maybe next time we can kick it off with the answer to that. But I think maybe Jack gets a lot of credit there. And Fortran optimizer, that might crack you up. Right here, Fortran. Who codes in Fortran? Fortran. Does anybody do it anymore? If you want to be quick, you would. It's still the fastest thing going. It's still your quickest system. So, but my real point is that Metropolis is at the top. So this is a foundationally important algorithm. I also want to show you another thing I worked on over the weekend. I ended up putting together a YouTube page for you guys. So I think I've got about 8 videos up. They'll be loading throughout the next couple days. I've done, I think, about half of them. But all you'll do is you'll go to YouTube, type in Believe in Lectures. So pretty self-explanatory. So my last name, Lectures. Just click on that and you'll get all the videos. So there are currently 6. I bet in the next 45 minutes another one will appear. So it's uploading on my computer. And so I didn't start with the syllabus course just to save some time. I'll probably put it on eventually. But they all start off like this. So sorry, my artwork is a little bit rudimentary. We are right in the middle of this discussion about competent person. So let's go back. So we are right in the middle of this discussion. They all start like that. Every single one of them starts about like a minute into the class.
Hey.
So I don't know why. But anyway,
I don't know why either.
This is our kind of first time through all of this. And so, but they are full-blown 50-minute lectures. Each video is one lecture, so apologies for all of that unprofessionalism. We'll get better in the next couple of years.
We're trying.
Yeah, absolutely. No, I mean, thank you very much to Sierra. Sierra Merckx has been back here diligently doing all of this. And the only reason we do it is for you guys. And so we don't really get all that much out of it. And so be nice when you go through and watch these. I watched a couple of them over the weekend and I was cringing and like, oh my goodness, this is really embarrassing. I need to lose weight. You know, it's like, it's really hard to watch. So be nice about the whole thing. It's public. If you want to send them to your friends, that's fine. Also, just a quick warning, they're not a substitute for class because I like this to be discussionary, that we can actually talk about it. And I think the Q&A and the review sessions are a big component to learning things. So this is meant to be reviewed.
I'm the first one to sum up.
What's that?
I'm the first one to sum up.
Oh, thank you. Oh, very good. Yeah, he likes. So I've got, like, I don't see it yet.
It's the first video. First time?
I don't see it yet. YouTube's a little bit slow, so I'll be looking forward to that. So.
If you like edit the title so that when you go to the top of that lecture,
Yeah. Oh yeah. So I can get you something there. Anyway, those are resources. So I said I was going to tell you what the Metropolis-Hastings algorithm is, but inadvertently I put it up on my title slide, right there. So I have 2 things up there. And so the first one you probably recognize. That's Bayes' theorem. That's what all Bayesians are doing. So some of the, more advanced Bayesian procedures are models where I can't write down what pi theta is, but I can simulate it on a computer. I can derive a process that kind of clicks through it. And that can be a very important thing. Of course, back in the 60s, you couldn't use that for anything. And so I can describe processes that I can't write down mathematically. So Dirichlet processes, Gaussian processes. So even this sort of point mass sort of thing can be hard to work through and marginalize depending on what your models look like. And I might need a process to estimate it all. That's different from the prior being a process. So sometimes we use algorithms to estimate things, and sometimes we use algorithms to express what we're even trying to model. The other thing that I've written down is an algorithm. And it has 2 steps in it. And so these 2 steps are to propose and to make a decision about something. And so a lot of times, I can mathematically write down what pi theta given the data looks like. I don't actually need to normalize it to understand that shape. So a lot of times we forego even writing down that integral. I don't want to normalize everything because that's the hard part of the calculation. It's where everybody had trouble a long time ago. But turns out there's an algorithm that I can use to sample from that distribution. And so this algorithm right here that I've written down is the Metropolis-Hastings algorithm. 2 very easy steps. And that's why this algorithm is probably so powerful. It's just 2 steps I have seen code where it's like hundreds of lines of MCMC to invoke these two steps, because you might have very complicated stuff going on. So there's just two steps. What we do, so basically I just want to point out that I'm using the functional form of pi theta inside of that decision rule. So it comes in as a ratio. So that's the posterior ratio. So I want to point out something before I even tell you about this algorithm. That if I'm evaluating that ratio, and that ratio in both the numerator and the denominator are being normalized, I don't actually have to work out the normalization constant. So if I take pi theta star, pi theta something else, so those are just two evaluations of pi theta. You can just think of them as two functional evaluations of this function. Don't actually need to evaluate the denominator, because it cancels each other out. So that's a beautiful thing. And so this is what gives this algorithm so much power, really, is I don't have to do any math to run it. And so I just need to write down what my model is, at least up to proportionality. Now, I've got this other piece, G, and I have to discuss what that is. So there's a proposal step. But basically, the algorithm in a nutshell is this wandering stochastic algorithm. And the whole idea is to obtain values of theta that represent its distribution. Okay, so basically I want to sample from a distribution. Let me just write down what the Metropolis-Hastings algorithm is. I'm just going to write these two things down again. So here's my goal. Sample from pi theta given our data. And I'll just write it down as x. So that's our whole goal. So basically I want values coming from this distribution. What does this distribution look like? Maybe something complicated. But to sample from this thing, usually I end up writing something down like this. So I want to sample some number of values. And I'll just write down t goes from 1 to cap t. That's our goal. So I want to sample cap t times. And I want all of these samples to basically form a histogram that looks like this curve. I want to point out something very important that some people don't get on the first shot. I don't know how to sample from this thing right here, but I can write it down up to proportionality. Those are two wildly different things. So I can write down a model on the chalkboard up to proportionality, likelihood times prior. That doesn't mean I know how to sample from it. Some people say, if you know how to write it down, then you know how to sample from it. That's the whole point, you do not. And so you could try to come up with schemas to do that, but this algorithm that I'm going to show you is one such general method for doing it. And so we want to sample from this thing. That's the whole goal. So here's the Metropolis-Hastings algorithm. This is the most general MCMC algorithm out there in the whole universe. So if you want to study MCMC algorithms, study this and you know them all. So you might not know all the properties until you actually define some of the notation. So here's what it looks like. It's going to be in for loop. T goes from 1 to cap t. So supposedly, I'm going to get cap t samples out of this. What I'm going to show you is going to be quite a little bit depressing that not all of the cap t samples can be used. And so what I'm really going to get is I'm going to get some number of samples that come from the distribution. After I get there and I start sampling from the distribution, I continue to do so. So it doesn't leave for a while. So at least they're well ordered. And there's just these two steps. So step 1 is to propose. And that just looks like this. I take a value of theta, and I draw it from some distribution. So what I'm going to do is I'm going to have some distribution. You're going to ask me which one, and I'm going to say that determines your whole algorithm. And so it turns out all MCMC algorithms vary by your choice of G. So I'm just going to start off real general about this. So I'm going to make it Markovian. So this notation is meant to suggest something Markovian. Considering where I was last time, so on the first iteration, this would be theta 0. And if you plug this into a computer, it wouldn't know what theta 0 is, and it would crash on you, or it would bark in some fashion. And so there is a 0th step up here. So I'll write down step 0 is to initialize. So I'm just going to set theta 0. And before we even do anything. So I have to plug in a number right there. That's my starting point. A very good number to pick would be a number in the middle of the distribution, or a number where most of the mass of the distribution is. If you did that, it turns out you would already be stationary. And all of your samples you could use as a sample from the distribution after you sort them. I'm going to have to talk about several issues that you have to deal with processing this stuff. But it turns out it's really easy, and if we've got a computer, it's a cinch. So the reality is we never know where the answer is. And so what we really want to do is we want to make our code robust to starting values. That if I start it very far from the truth, it should come and find the truth eventually. Okay, so from an engineering standpoint, I would say we want to set this very far from the true answer and make sure our algo works and converges to the right thing. But in a mathematical sense, I would really like to start this where the answer was. And so that I don't have to waste a lot of time finding it. What I'm going to tell you to do in practice is do both. So to bulletproof this thing. So what I'm going to do is I'm just going to sample from some value right here. Here's kind of a pictorial of a very easy thing you could do. I could say, given where I was last time, theta t minus 1, I could end up coming up with some g right here. And this might denote its density function right here. So I might say, I'm going to look in the area where I was last time, plus or minus some noise. And so I might select out of here this value right here, and I might call that thing theta star. So I'm just sampling from this distribution. This sort of proposal, so we're proposing a value, it's called a local proposal. So it's kind of what you've seen is probably the most convincing stuff. You know, I don't like to tend too far away from my answers. So I will give you a hint that good algorithms have the ability to search and exploit what they found, and also have the ability to explore new horizons. So it can get out there and move around a lot, but also exploit what you found. This proposal does only one such thing. It only explores locally. How far? Well, it depends on what I pick G to be.
When you're talking about exploiting and exploding, do you really talk about like Q learning and reinforcement learning, or is that?
No, but all good algorithms. So whether or not you're maximizing a space through like Q learning or something like that, all good algorithms have two good properties. So I don't mean that as only MCMC. So if you're trying to find something, you want to sit there and be able to refine around good stuff that you found, but also explore so you know that you touched on most of the space. You want to do it in such a way where you don't actually have to exhaust the space. So all of these algorithms, for any maximization algorithm or any algorithm for sampling, they'll both do these things. So they use those terms too. So here's step 2. and I might finish drawing this, and say maybe there's a parameter you might pick right in here to, control how much you're willing to deviate from where you saw last time. And so this would be like a tunable. I'll give you mathematical descriptions of these things in a moment. These are just ideas so far. So step 2 is to decide. And this is how we do it. So I'm going to show you the Metropolis-Hastings decision rule. It's this. So I'll just write down alpha. This is actually going to be my acceptance probability. So that's really what Metropolis-Hastings is doing, is it's trying to figure out what the correct acceptance probability is. So what we're going to do, just conceptually, before I show you the rule, is I'm going to propose to move somewhere, and I'm going to do one of two things. I'm either going to stay where I'm at, or I'm going to make the move. So I propose, and I make a decision, should I stay or should I make the move? This is what we use to calibrate the decision probability. This will do the right thing for us. So this is going to be the minimum between 1 and some other positive number. So let me just write this down right here. It's going to look like this. Pi, theta, star, given our data. Remember, this is our density that we want to be able to sample from. So I can write this thing down up to proportionality. And I'm going to compare it to where I was last time. So I'm just plugging numbers in to that function, or up to proportionality, that function. And then I've got one other bit right here. Looks like this. G theta star given theta t minus 1. G theta t minus 1 given theta star. So at least conceptually, this isn't a difficult thing to evaluate. So that's what you should be convincing yourself of right now. Both steps are relatively easy. I'll show you the last bit. I haven't shown you what to do, but I've told you, either you move to that location or you stay. You stay put. So, but there's 2 steps. I sample from some distribution. I'll talk more about how you get this, but here's at least a visual starting point. And then I make a decision. So I evaluate my posterior up to proportionality in 2 different spots, and then I evaluate my proposal in 2 different spots. Keep in mind, this is the inverse of that. So this is being evaluated at theta star. This one's being evaluated at theta star. This one's being evaluated at theta t. This one's being evaluated at theta t. These are conditions, so that's a little bit different how we're treating that. The last bit that we do is we just update theta t. So I'm going to make a stochastic decision based off of this number right here that I'm calling an acceptance probability. You should also convince yourself that this alpha right here is a number that lives between 0 and 1. So it's capped at 1. And this number right here is always positive. These are density functions.
So if you reject, is theta t minus 1?
Yes, absolutely. So easy stuff. So Dan wants me to get to the point. So this is going to be either theta star, or it's going to be theta t minus 1. This is going to happen with probability, alpha. And this happens with probability 1 minus alpha. So all I do, again, propose, evaluate, now flip a Bernoulli. Plugging in alpha as your probability. And then I either move to the new location, what I've proposed, or I stay exactly in the same place. So three steps, maybe you might say. Pretty easy. Anybody in the world could code this thing up without even understanding what it exactly does. What it does, so here's a fact. If G lives in the same space as pi then eventually, this is important, the algorithm samples from pi theta given x. So let me draw you a picture of that. Let's say, imagine pi theta given x, where theta is two-dimensional. So I've been drawing everything out as one-dimensional. Let me draw it out as two-dimensional so you get more of an idea of what's going on. I have more choices than just to move left and right. So imagine I've got some distribution. Here's theta 1, here's theta 2, so those are my two dimensions of theta. And what I'm going to do is I'm going to start somewhere. So I'm going to call this theta 0. What's going to happen is in our first iteration, I'm going to either stay in the same location or I'm going to make a move. Say I made a move. Theta 1. Say I make a move again. Theta 2. It's not even close to the right place. So it keeps moving far away from my starting location. And then eventually, it starts moving around here. So that's about what it looks like. We'll look at my code again and run it and see what's going on. But this is what the algo does. And so this part of everything is called burn-in. And so what we typically do is we rip this stuff off. This is the eventually part that I wrote down. And it starts hovering around an area right here. This is called the stationary distribution. So here's what this fact really says. Pi theta given x is the stationary distribution. Of the Metropolis-Hastings algorithm. So how many of you know something about Markov chains? All of us at least have some idea of what they are. Let me just write down the definition real quick. So just briefly, we're moving through some space. I'm going to talk about my space through time. That's why I've used t. But if you don't like that, just call these iterations. Okay, so change it all to i's. So I have a Markov algorithm right here. What it means is that through time, I only consider the answer at the previous time step. I never consider anything further back in time. So that's the Markovian property. Markov property. Only consider one time step back. I'll make a note, if you go farther back, it's not Markov. let me be a little bit more specific mathematically. So there's some probability in here of moving from theta star to theta t, whatever it is, right? So this is a probabilistic thing. And so this is a stochastic algorithm. And so if I ran this interior thing over and over again, I'd always get different answers, right? There's some probability of moving from one answer to the next. Let me clean up my language. There's some rate of transitioning. If pi was continuous, I don't mean, bless you, I don't mean probability. There's no probability of moving from one thing to the next. It's always 0. But there's some rate at which I can do it. So I can talk about that probability as an instantaneous rate. That's the density function that allows for it to move. So, but there's really two different parts to this. If pi was continuous, I've got a continuous part, and I've also got a discrete part. And so I'm a little confused on my language. What do I want to use? Do I want to use probability or do I want to use density to say how fast I'm moving there? If it were purely continuous, I'd say density. And if it were discrete, I would use probability. But I've got 2 bits right there. And so I'm going to change my word to rate so that I don't say things that are incorrect about probability spaces. So let me just write this down. There's a rate. At which we transition through, I'll say, data space. And I'll just give it some notation. Rho, that's my rate. So rho. Theta t given theta t minus 1. I'll just write it down like that. So incrementally, in every time step of this algorithm, there's some probability or continuous form of that or mixture of it, some rate at which I transition between these time steps. Okay, and we can quantify it. How do we do it? We stare at the algorithm and we look at what we've done. These steps are conditionally independent of each other, so I just multiply them together and I get that rate. We'll do that soon. And I'll say rho theta t given theta t minus 1, theta t minus 2, theta t minus 3, all the way back to theta 0 is equal to this. That's the Markov property. That's what it means to be Markov. So if you wanted to write this down mathematically, you'd do it this way. If you wanted to tell somebody what it meant, I only used the answer at one time step back. And so this information right here is contained in that information right here. That's saying it's Markovian. So it turns out all Markovian transitions, so really you could, if this was discrete, you could enumerate a big matrix showing how you transition and what these numbers are. Our thing is continuous in nature, and so I can't write it down in a matrix. But all Markovian transitions, the whole process, have stationary distributions. And it turns out, what you might learn in a class, if you've ever taken a Markov Chain class, is that some of them have limiting distributions, meaning that I can just click through that distribution, transition through it over and over and over again, and the probability of being in a particular state will start to settle down. And so that's kind of a neat thing. I need to tell you a little bit about that stuff and all that mathematical, all those mathematical properties. But I'll just write this down. All Markov processes I mean by a process is just going through the steps and generating it. That's all I mean. So even like flipping a Bernoulli or coin is a process. So this is a little bit more complicated than that. So all Markov processes have stationary distributions. So just be a little bit upfront with the math and we'll get to it later. We really want to get down to the algo and run this thing. Here's what it looks like. So stationary distributions, and I'll just call it pi, theta. Okay? And so what it ends up looking like is just this. Rho theta t given theta t minus 1, pi theta t minus 1, d theta t minus 1 is going to be equal to pi theta t. This is what it means for a distribution to be stationary. Let's just look at this equation. So I'm just taking this as a concept right here. We will derive soon enough that this algorithm adheres to this. If we can write this down right here, and it turns out the stationary distribution is going to be our posterior in this. But what it says, and what I want to be really specific about, because a lot of times I break this rule in my class, that everything I denote with the same letter means something different, right? So I always use F or L or something like that. What I mean is this is the same function. Same distribution. So this is a distribution on pi, right here. So what it says is if I sample out of this, sample from here, I plug it into my transition rate, I get something out, and I integrate over all possibilities right here, I come back to the same function, it's just evaluated at a different spot. So what I mean, I've got some function right here, this is pi, this is theta, and this might be theta t minus 1 right here, and this might be theta t. The same distribution governs both of these things. That distribution isn't moving.
What's the difference between G and rho?
G is part of rho. So also, so is this. So is my whole decision rule that I erased. I will write it down for you specifically soon. So G is a part of rho. Okay, what it really is it's G times alpha. So that's what rho is. Okay, so this algorithm is a Markovian algorithm. This is what a stationary distribution is. This is a hard calculation to usually do. If I give you a process, find the stationary distribution, usually a hard thing to do. Notice what we're doing is a little bit different. I know what my stationary distribution is walking into this. And I'm constructing an algorithm to sample from it. I'm constructing a Markov chain to iterate so that eventually I obtain samples from it. So entirely different from what you would do in a stochastic process class. In a stochastics class, they would tell you the Markov chain, transition probabilities, and your job is to figure out the stationary distribution. So kind of remember this, lots of little problems surrounding that. What we're doing is different. I already know what my stationary distribution is, and I'm constructing a Markov chain so I can click through and sample from it. So let me just write this down. Some Markov chains have limiting distributions. What I mean by this, and I'm just going to tell you in words and later on I'll write it down mathematically for you, means that if I just click through, so iterate through, rho theta t given theta t minus 1. So what I mean by this is start somewhere, get a new value. Take that new value, plug it in right here, get a new value. Take that thing, plug it in, get a new value. just keep doing that over and over and over again, turns out the probability or densities of being in a certain state will converge. Only some Markov chains have that property. Turns out if they do have limiting distributions, the limiting distribution is stationary. So I've told you a lot of technical stuff. You need to go through all that. I want to get it out of the way so that when we come back around to it, all these words aren't brand new to you. So here's the fact. If a Markov chain and the Markov chain is defined by this, defined by rho theta t minus 1 given theta t, has a limiting distribution. The limit is stationary. Okay, so turns out if G is well constructed, this will have a limiting distribution, and that limiting distribution will be stationary. So let me say my punchline real quick before we do something practical with everything. This is a Markov chain, and all I'm doing is clicking through it. I'm just running it, and I'm going to make this thing really big so that eventually my probability of being in particular states is settled down. Okay, it's converging to something. And it turns out that that limiting convergence, those samples, are stationary if G is well constructed. And I'll tell you the 3 conditions we need on G, or we need on our whole chain to do this. And so G has to be constructed in a particular way. So, algorithm, easy, running a Markov chain till it limits, which is stationary. And it turns out this construction of Markov chain samples from our posterior distribution. That's what it ends up doing. So that's the whole name of the game right here. So a couple things to remember, easy algorithm to code. If it's well constructed, it converges to the right thing. About a week's worth of math to explain to you. Any questions? Is that just puzzling?
So if only some Markov chains have limiting distributions, then for the others, will we find ourselves hitting that stationary distribution and deviating from it as the process continues?
It might not even get there. So might get stuck somewhere. So here are the 3 conditions. Okay, I'll try to make them make sense. That you can always keep moving around. You don't get trapped somewhere. Okay? So you can keep moving around the space. I can move from anywhere to anywhere else in the space. So I have the potential to do that. It doesn't have to be in one move. It has to be eventually. And I can always come back to where I started from. So I don't just slowly drift away from it. So I can come back. I can get from anywhere to anywhere. And I don't get trapped anywhere. There's one other part that I don't do things systematically. So I don't have repeated patterns in the way that I do it. It has to be random. And so that's the idea of aperiodicity. So we'll get those technical terms, but it basically means that if I can flow around the space, I'll learn. So kind of obvious, sort of conditions that we need. Those are called the ergodic conditions. So that's called ergodicity. So we'll go into all of it, but I think these are the 2 main ingredients to being a good Bayesian. If you understand these algorithms, so I'll go into a little bit more detail than I used to go into in this class, and try to build in some of that Markov theory for you, and show you how to apply it to big stochastic models. Let's just go back to our earlier example. And it turns out I did have an error in the code that I was using. So in my examples, I actually was plugging variance in to plot the truth. So my truth was being plotted incorrectly. The algorithm was working correctly. So let me just show you right before we leave to show you my variant of the code. I'm going to show you what I would write down. I'll show you what I would actually code up if I were you. But let me just show you and remind you what we were doing with this thing. So all I'm really doing is just following those two algorithmic steps. And I'm plugging in for those two algorithmic steps when I have that minimum of 1, the ratio of the posteriors, so I'm just plugging in my posterior up to proportionality. I'm going to show you a bunch of details in here. Turns out I don't actually ever plug in my likelihoods because it can be extremely unstable. Instead, I plug in my log likelihoods. And so I don't like taking ratios of things with ease because it tends to blow up on a computer. So I've done a lot of work to work on a differencing scale and not a multiplication scale where I'm dividing possibly by small numbers. And I'll show you how I do all this sampling later on. But in my code, I have a bunch of logs built in there so that my code is robust. So it turns out evaluating that alpha minimum of 1 ratio of the posteriors, inverse ratio of the proposals can be numerically unstable. So I've gone through a lot of work to prevent that. And then everything else in my code is plotting. So let me just remind you what we did with the code last time. What I did is I'm trying to sample from this model. I like to sample from pi, phi, mu, given all of my data. This is precision, that's mean in a normal model. Same example that we were working with last time. I'm going to generate some data. Let's get some new stuff. Looks like they'll let me forbid for 9 more times, so we're good. And then I'm just going to sample some stuff. I'll put a semicolon at the end, not print to screen. I'll speed everything up. I've already got a true sigma, a true mu. I've plugged in those numbers. Turns out I was handing it variance, which was always smaller, you know, because I'd square it up again and push that thing really over. And so, and this is what the algorithm ends up producing. So again, we've got our burn-in phase, but all I'm doing is I'm running a Markov chain to limit. And so in the limiting answer gives me, you know, what I'm after. So what I'm going to do is I'm going to chop that thing off. So it turns out this equation right here, in this part of the burn-in, right here where it's transitioning, these have not converged to pi, the stationary distribution. So I keep moving. So I'm sampling from the wrong thing. I'm too far into the tail. And so it knows. Eventually, when I settle down into this region, I start sampling these values right here. And these values are governed by this function right here. So that's what we're actually doing. How am I doing it? By iterating through this thing. So pretty neat. So a lot of machinery, a lot of technicality in there. I think we'll do about a week of Markov chain theory in here so we can understand these algorithms so that you'll be at a level that you can build your own. I think that's the real goal. So we'll come back next time, continue with this. I'll walk through technical details of my code, and we'll know MCMC at the end of about 2 weeks. Thanks, you guys.